The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. Welcome again to the second session of this webinar series in September. And today we'll be talking on curved steel girder bridge. Those who are listening to me for the first time, let me introduce myself to you. This is Arun Sharma from Midas, and I'll be covering this session for you. So we'll have a short question answer session towards the end of the webinar, so you can hold on to your questions and then use the chat windows that are there to communicate with me. I have muted everyone's mic so that I can reduce the noise coming from the other ends. I think it's time now and we are good to start. So today, as I mentioned, we'll be talking about steel composite curved girder bridge. And this is the overview for the bridge. We'll be first starting by defining some materials and sections. Then we'll create the geometry from scratch. I'll model the cross beams and the diaphragms into the structure. Then apply boundary conditions. Boundary conditions will include the definition of rigid length, elastic length of rigid type, and the support conditions. Then we'll apply the self-weight and the superimposed dead load onto the structure, followed by the live load application. For this, we'll create two lanes, and they will carry vehicles in both directions. We'll have HL93 vehicles as per AASHTO LRFT, and in this I'll also try to cover response spectrum analysis as well as live load analysis. After this, we'll perform the analysis and review some results. This is the plan of the bridge that we'll be modeling. As you can see here, it's a 200 feet long bridge and has an offset of 30 feet. It's a 3 girder system, and the girder to girder spacing is given to be 10 feet. And at the end, it has a rotation of from the main or from the global axis direction of 30 degrees. So what I'll do is go into the program itself and start the modeling. So let me start with a blank sheet here. I'll go to the works tab as a thumb rule so that I can see what all things have been applied to the model so far. I'll right click, go into properties, and click on materials to define the material properties. I can click add and then select the relevant steel material I want to use, the standard being ASTM and the material be A70950W. Click OK, and then so on and so forth. I can go and define materials, but to save time, what I'll do today is bring in the material properties from a similar project where I have the materials already defined. So I'll just bring the materials and sections from the completely model file. This 3 set of materials. I'll click OK and I'll import them. I'll come to section tab and import the sections that I'll be using from the same source. Or no, I don't want to import these. Let me open a different file. Yeah, probably this one has more sections that we will be using, and I don't want to import this section for the time being, so I'll take this out. Basically, in the section list, the program shows you all the sections that are there in the model file that you open, and you can then choose which ones you want to be imported. So I'll just import all all 9 except this 8th section. So I'll select it and take it out from the selected list. You can choose to have to keep the original IDs as 1 2 3 4 5 6 and 9, or you can start by new ID and that will renumber them as 1 2 3 4 5 6 7 and 8. So you can choose out of the two options. I'll choose as the default one. And if you happen to have a list of elements of your own, let's say a list of sections of your own, let's say you have element 1 2 3 4 here, and if you choose to keep the IDs, then the existing sections will be replaced by the new section IDs. So you have to be a little cautious while you are doing this kind of import. Click OK, and now you'll see the sections that we have brought in. So if I double click on the girder section, you can see its property. It's a composite girder that we have defined with the concrete deck and steel girder. We have used a section offset and set it as center top so that we can model the cross frames accordingly. If you double click, this is the diaphragm section, which is happens to be I girder, and so on and so forth. We also have tapered sections for modeling the pier elements, and for this I'll just click on the tapered section that we have. So it is P_L. This is the tapered section that will form the pier cap left end, and you can define the dimensions for the two extreme ends of tapered section. So tapered element. So this is the, let's say, I end, this will be the J end, and you can define how you want to taper it. So the y-axis, as you can see in this plot, y-axis is the horizontal axis, z is your vertical axis. You can choose how they are to be tapered, linearly or non-linearly. You can select from different variations. For the timing, we'll stick to linear, and depending upon where you choose to have your section offset, the depth or the tapering is done. So if I choose the section offset at the center top, then the depth will be varied. So basically this section offset line will remain as it is, and the variation will be done about this point in the cross section. So if I have the section offset at the center point, then it will vary depth equally on either side of this centroid. And if I have it at center top, then only the depth will be varied under this point. Things will become more clear when I start modeling it, and you will get a better visualization of it. So I'll not invest much time on it right now. So these are the sections that we'll be using, and I have defined a dummy crossbeam for modeling the deck. The thickness of the dummy beam happens to be equal to the thickness of the deck, and the width being the spacing that you want to apply the dummy beam. It will be modeled based on grillage concepts. So the parameter B is at user's discretion, what spacing he wants to have and how much width he wants to give. And I have used a crossbeam material which happens to be weightless, because you can see the weight density set as 0, and I'll be adding the weight of the concrete or the deck using the composite section itself. So I just want to have the stiffness in the transverse direction for the deck. Therefore I'm using the crossbeam material as weightless. Now moving on with the modeling, so I'll right click, go to nodes and click on create nodes. I'll switch to the top view and I'll change the length unit from inch to foot, and here I'll go and enter the coordinates that I want to create. So I'll enter here, repeat or copy it once, and create it at 200 feet along global x-axis. The moment I hit apply, and use the zoom fit button, you'll see two nodes on your screen. I'll create another node and change the number of times to 0 because I don't want to copy it. I'll create the node at 100, 30 feet and then click apply. So you can see 3 nodes are created in the plan. Now I'll select all the 3 nodes that are created by clicking select all and right click, go to nodes and translate them. So since I mentioned the girder to girder spacing is about 10 feet, I'll translate them along y-axis through unequal distance, first 10 feet, then comma, minus 20 feet because these are the incremental distance. So I'll click apply and you will see that the other set of nodes are created. Now the nodes are rotated about 30 degrees about the origin at this for this abutment. So I'll right click, go to nodes and rotate them, and in rotation the mode will be moving the nodes. I don't want to create a copy, and enter the angle as 30 degrees. About z-axis I want to rotate and the point of rotation will be origin. I'll click apply and you can see the nodes rotated. Then I'll select the other set of nodes and enter the angle of rotation as minus 30 degrees, and the point of rotation will be the center point of the other abutment. So basically what I did is I clicked in this field, it will turn green. This means it is an active field and it will take the inputs directly from the model view window. This is the model view window that you are looking at. So I need not remember the node number or the coordinate number, coordinates of that node. If I just take my cursor to that node, you can see the coordinates are automatically updated in that green field. I'll click here and it will be registered, and then I can click apply and you can see the rotation done. And I will request everyone to hold on to the questions towards the end of the session so that we'll have some time to discuss all the questions, so you can note it down with yourself and then we can discuss it. And if we are not able to take up all the questions now, then feel free to drop me an email and I'll reply to each and every individual. Now moving on with these nodes generated, I'll right click, go to elements and select create line elements on a curve. This feature allows you to create the geometry, a curved geometry. As you can see, the curve type is arc by 3 points. There are other methods also available. You can choose the method most suited for you. So we'll choose arc by 3 points because we have 3 points on this arc to generate the complete curve. And I'll select the material as steel and the section as girder, and I'll have this curve divided into 40 segments, and I just need to enter 3 points which lie on this curve. So I'll just click on the field P1, click on the first node, then directly move on to the second node, and then move on to the third node. And you can see the curve is created and divided at the 40 points into 40 pieces. Now I'll continue creating these other 2 girders. Click on P1, P2 and then on P3. Then I'll repeat this for the third one. And you can see that the program is able to generate the curve based on your 3 points. I'll just press down the control button from the keyboard, hold down the wheel mouse button and rotate the structure dynamically. So now here you can see the geometry in the rendering view. Now having done this, I'll switch back to the top view and activate the hidden view, or deactivate the hidden view, so that I can see the wireframe geometry of the structure. And now I'll create the diaphragms onto this girders. So right click, go to create elements, and here I'll select create general beam, material being steel, the section being diaphragm, and I'll click on nodal connectivity and just click on the first node and go all the way across it and click there. The program will create two elements and divide them at the nodes. So this was the first abutment. Then I'll come to the pier, and if I just place my cursor, I can see the cursor location in the status bar at the bottom of the screen. So you can see the coordinate as 100, 10, 20, 0. This means this is center point. I'll create another diaphragm here and the last one at the other end. So once this diaphragm is created, I'll change the section to bracing and model the cross frame top chord, which happens to be at every fourth interval. So I'll just quickly create them. I'll leave 3 nodes and go to the fourth one and create it. So in this manner, the basic geometry is ready. Now I'll show you how to model the 3D cross frames. So for this, I'll click close here and just activate the diaphragms and press down the control button and double click on the bracing sections, so you can see them, they are highlighted on the screen. And then I'll click activate. The moment I do this, you can see just the relevant members activated on the screen. And let me first show you the geometry of these diaphragms. So this is the diaphragm, as you can see from on the screen. This is the top chord that we have already modeled. Then we have to model a bottom chord and get the truss members in. So what I'll do is translate these top nodes by the depth equal to the web height and create nodes at the bottom, and then connect the bottom chord and then draw the truss members. So I'll switch back to the model itself and first select the diaphragm members along with their nodes. Right click, go to nodes, translate the nodes through equal distance. Mode should be copy, not move, because we are just want to copy the nodes. And the distance should be 76.8 inches. So I'll change the units from foot to inch, and the distance I'll enter as 0, 0, 0 minus 76.8, and then click apply. Then I'll select the remaining bracing members along with their nodes, and they will be translated by 74.4 inch, and then click apply. Now if I rotate the structure dynamically, you can see the nodes that are created right underneath it. So what I'll do is go through the definition of one diaphragm and one cross frame, and rest will be done in the same manner. So I'll right click, go to elements, create element. I'll select steel material, section being bracing. The bottom chord for the diaphragm is made of bracing member. Click on nodal connectivity and then just click on the bottom chord nodes to create the bottom chord. And now I'll create the truss member. So I'll change the element type to truss. Section and material properties remaining same, and I'll click on the nodal connectivity. Now I need to connect this node to the center of this element, or the midpoint of the element. Now if you'll see at the corner of this screen, on my left hand corner, right hand corner, you will see a number 2 written there. This means the program will automatically snap a node at the midpoint, or divide one element into two pieces. If you want to have the element divided into three pieces, you can have this number as 3, 4, 5, so on and so forth. So I'll click on the nodal connectivity, click on this member, then move my cursor to somewhere in the midpoint. The program will automatically snap a node at this location and create the element and divide the other element. So let me zoom in at this location so that you can see more clearly. Now I'll continue to create the member. The same manner I'll create. So this is how one diaphragm looks like. Now I'll create a cross frame. So I'll change the material element type to general beam, and then click on nodal connectivity, and then create the bottom chord first. Change the element type to truss, and this time, since it's a cross frame, I don't want the truss members to be intersect and have a node in between, because truss members cannot support bending moments or bending out of plane bending. So if we have a node at the intersection of truss members, then it will result in singular errors. So, but still, I want to have them in the cross shape. So I'll check off this option called intersect at nodes and elements, and then click in nodal connectivity, and then I'll just click on the top node, then on the other end click and click. So now you can see the element is not divided at this location. Same way, I'll click on the two ends and create a cross frame in no time. Now as you can see, these two nodes are in the same plane and happen to lie on the same web, but they are not connected to each other. So for this, we'll use a boundary condition called rigid link. So what I'll do is right click, go on to properties, and select rigid link. And as we know, rigid link follows master slave node behavior. So the node that will govern the other node's behavior should be made as master. Since our diaphragm, the bottom nodes will have the boundary condition assigned to it, and we want it to govern the behavior, so the bottom node will become the master node. So I'll click in the master node number, and then let me check off, toggle off the single select tool. So I'll click in the master node number, it will turn green. Then I'll go to the node and then click on that node. The moment I do that, the master node number will be read by the program. Then I'll go on to single select tool and select the node that has to become its slave. And then I can specify what type of link I want to have. It has to be a rigid body behavior. Then I'll click apply, and the program will generate this rigid link. So let me quickly repeat this step so that you understand how to create a rigid link. So I'll select the slave node by a single select tool, then click in the field for master node number, and then click on the master node. So it will read the number as 124, and then click apply. I'll repeat, I'll use single select, I'll select the slave node, I'll click on the master node number, select the click on the master node, click apply. So in this way you can generate master slave node, rigid link between master slave nodes. The master node is shown by number 11111. This means it's a rigid body. All degrees of freedom are of the slave node is restrained to the master, and on the end you'll see this degrees of freedom written is called the master node. But for the intermediate locations of this cross frame, we want the girder, basically the node that you see at the top is connected to the girder. So we want this node to control the behavior of the bottom node, since all the loadings and everything is applied on the top of the girder, or on the top node. So we'll make the top node here as master and use single select to select the node at the bottom, and then click apply to create the slave node at the bottom. So you can see how this rigid link is created. I'll repeat this step. Select the slave node and the master node, and then click apply. Select the master node and the corresponding slave node, and then click apply. So in this way you can create rigid links and model your cross frames in 3 dimensions. So what I'll do is now open a file number 3, in which I have already modeled the diaphragms and the cross frames with the rigid links, and you can see them in this layout. I can just right click on any of the rigid link and select display, so you can see the the master nodes at the 2 abutments and the slave at the top in the intermediate sections. And you can also notice that at the pier section we have not modeled any links, because we will be modeling the bearings, and we will be using different type of link elements at this location. So now let's start the modeling at the pier. So what I'll do is switch to the plan view, and let me undisplay the rigid links for the time being. I'll right click, select undisplay, and then use single select tool to select the particular plane so that I can select few girders and the nodes underneath it, and then let me click activate. I'll switch to the front view. This is the elevation, the left view, where you can see the cross section at this location. If I switch the solid view, you can see that this is how it looks like. The girder, the nodes are at the bottom, and now I'll translate the nodes for the bearing height and then model the pier cap underneath it. So let me select those nodes first. So I'll select the bottom of the 3 girders, and right click, go to nodes, translate them through equal distance, and the distance in the z direction will be minus 12.4 inches, and click apply. So you can see the nodes created here. Now let me first show you the pier cap. So our pier cap looks something like this. I mean, I'll taper this. It will finally look something like this. So it will have a tapered ends on either side and a flat section, or the non-tapered cuboid in the middle. And so what we need to do is need to get these nodes into place from where the tapering actually starts, where the bearing location is there. So what I'll do is select this particular center node and translate the nodes to get the other locations, and this information can be very easily extracted from your CAD drawings or your PDF drawings where you want the nodes. So I'll go back into the program and select this node, and I'll translate them through unequal distance. And if I go to the plan view, you can see that I want to translate in the global Y direction, so I'll just select Y. Let me switch back to the side view and enter the distance as minus 36 inches, comma, from that location go minus 138 inches, comma, from that location go plus 210, and from that location go plus 138. And when I click up, the negative distance being on the right side for this display, and positive being on the right side, sorry, on the left side. Then I click apply here, and you can see the nodes created. And now I'll go to right click, elements, create element, select the concrete material, select the element type as beam, select the section as right end of the pier cap, and then click in nodal connectivity, click on the node, and then click on the other end. Now you can see that the section, since we set this offset of the section at center top, and we gave in the program while defining this taper section the cross section of this end and the cross section at the final end. So the program created a tapered section with these two dimensions at the two ends of the element, keeping the top line as constant and varying the height underneath it. So this is why the section offset, this is where the section offset plays a critical role for defining the tapered sections. So now I'll change the section to peer cap center and then click on the other set of nodes to create the center peer cap, and then we have the section on the left end and it will have the taper in the reverse direction. So now we'll use a feature called taper section group that will smoothen this curve or the transition by interpolating the height of the section at the intermediate length, because the we know that we can see here this should be the final the depth at the final depth at the let's say the jth end of the member and the ith end of the member, and when we divide this into number of pieces, the program will automatically interpolate the height of the member in between to make a smooth curve. So for doing that, I'll just right click, go to the properties and select tapered section group. I'll enter the name as peer cap let's say R for the right side. I'll use single select tool and select the two members on the right side. I can set the variation as linear or polynomial, the z-axis being the local z-axis for that element, which is the vertical axis, and I can choose it to be a polynomial curve, whereas the y-axis happens to be the horizontal axis for this cross section, as linear. And then I'll click add, and you can see the program has interpolated the depth of the section and made it a uniform tapered. Same thing I'll do at the other end. I'll change the name after selecting the members that I want to taper as peer cap underscore left end, and I'll choose the from jth end I want to have this polynomial curve, and then click apply. Let me undo this and show you what will happen if I choose the symmetric plane at I end. Let me select the previous members, peer cap at left end. If I select in this manner and click add, it will have the taper the polynomial curve generated in the other direction. As you can see, this is concave, this will be convex. So I'll select this and modify to back to J and click modify, and it will modify. So this is how we generated the peer cap. Now I'll select this node and create a node at the bottom of the peer cap to model the peer underneath it. So right click, nodes, translate, and I'll copy the node through z-axis, or let's say just equal distance. The depth of the peer cap is 6 feet or 72 inches, so minus 72 I'll enter here and click apply. So I'll get a node at the bottom of the peer cap. I'll select this node, right click, go to elements and extrude elements, the type being beam, material being concrete, and the section being peer, and I'll give the intervals as minus 62.4 feet 4 inches and repeat it 5 times. Click apply. So if I zoom out, you will see the peer created underneath, and this is the peer cap that is modeled. Now if I switch to the wireframe geometry, you can see that these nodes are not connected with each other. So I'll use properties and go to elastic link and select elastic link or rigid type. Now a common question at this point is what's the difference between rigid link and elastic link of rigid type? Basically, the members, whenever you want to create with infinite stiffness, both behave in the same direction. But for rigid links, you need to have a master and slave node behavior, and they cannot be applied in a sequence. Let's say if I want to have 3 links in this plane, it will be difficult for me to define as master slave master slave master slave, because if a node is if one node is master, it cannot be slave to another node. So there are some technical issues while defining them in series. The second thing is, whatever boundary condition we assign at the master node, it is replicated or copied at the slave node location. So you should be little cautious while defining the rigid links at the boundary location, like at the end diaphragms. If you want to simulate, not replicate this boundary condition onto the top of the girder, and if you want to have the real effect of the barrier, the bearing location or the support and the height of the section, then you should use elastic link of rigid type for those locations. One more thing that elastic link plays a good role in is, you can control the stiffness in different directions. So if you want to model let's say an expansion bearing, you can control the stiffness along those axes and then model it. But today we have fixed bearings, so I'll not be dwelling much into generating the bearings there. So I'll just select elastic ring of rigid type, click on two nodes field, and then just click on the nodes between which I want to create it. And if this is my node, this is my direction of creation of the elastic link, then this is node 1 and this will be node 2. So the direction becomes x-axis, and you can see if this is x, the y will be this one through from right hand thumb rule, and z will be into the plane of paper or this screen. You can select to copy the elastic link along y-axis and to at 120 inches, because the distance between these points is 120 inches or 10 feet. So I'll just click on two nodes and click between the these two nodes, and the links will be created. Basically, this is the location where you have the bearings. So if it was expansion bearing, I would have selected general type of elastic link and control the stiffness along these local x, y, and z axes for displacement and rotation. But since it's we have a fixed condition at the pier, and we have expansion bearings at the two extremes, that means at the two abutment, I'll have fixed bearing at this location. I'll use the same elastic link of rigid type for connecting the bottom of the girder to the top of the girder. Click on this two nodes. When I do that, you can see the nodes are the elastic links are created and copied at the same time. Now I'll activate the entire structure, which completes the modeling of the links. And now I'll switch to the top view, and as I mentioned, we'll have the grill edge concept applied. So you can right click, go to elements, create elements, and start creating cross beams using the cross beam material, which happens to be weightless. So I'll use dummy cross beam, click on the nodal connectivity, and then go on creating the cross beams like this. So what I'll do is open the next file that I have here, which will have the definition completed, file number 5. So now here you can see the cross beams have been created, and you can see also the support conditions have been defined. So what I'll do is quickly delete them and show it to you how they are defined. I'll also delete the loading conditions that are there. So defining supports is pretty simple. Right click, go to boundaries, go to support, and select the degrees of freedom you want to restrain at a particular node. So I'll restrain the dy and dz at the two abutments and the exterior girders, and these dy and dz are in global direction. If you want to apply these restraints along the curve, then you can easily rotate the nodes and change the nodal axis and apply them along that direction as well. If you want to do that, I'll show it to you in a little while. I'll select the 4 nodes, click apply, then I'll select the center node and select the direction as dz, that is to be restrained. Click apply. The symbol in itself is explains what degrees have been restrained. From 12 o'clock to 6 o'clock, dx, dy, dz are 3 displacement degrees of freedom. Whichever is restrained is shown in green color. Whichever is released is shown in white. So you can see dy and dz are restrained at this end. The remaining 3 are rx, ry and rz, which means 3 rotational degrees of freedom. Since they are all released, it's shown in black. And at the base of the pier we'll have a completely fixed rigid support, so it will be all displacement degrees and all rotation degrees will be restrained. I'll select the bottom node and click apply. So in this way you can create the support conditions. Now coming back, if you want to change the nodal axis, you can right click, go to node, and come to the boundaries because it's related to the boundary function, and click on nodal local axis. Now you can select in which way you want to define the nodal local axis. So I can go for 3 point. I'll come and click at the origin for that plane. Then my next point should be on the x-axis along that direction. So this will be this point, and then the other point that will be any point on this plane will be P2. I can click on this point and then click apply. So basically what I did is I applied this point at x, this point along x-axis, and this point in the plane. So it will be x, y and z for this node. So I'll select this node, I'll select this node, select this node, and click apply. So the moment I do that and zoom in, you can see x, y and z for the nodes are rotated, and hence the support will act now along x, y and z along this curvature. Same thing you can do at other ends and rotate the nodes if you want, but this is just meant for demo, so I'll revert back to the previous condition. And now I'll go ahead and define the load cases. So click on load and then select static load case. You can enter the name of the load case as self. You can select the type of the load case as dead load, and then click add, and then you can enter the name and select the type as dead load, and then click add. So we have defined 2 load cases, self weight and superimposed dead loads, and now I'll add values to them. So right click, go to loads and select self weight. Here I'll add the multiplication factor as -1 along z-axis. Then click add, and then I'll right click, go to element and go to loads and select element beam load and select superimposed dead load. Here it will be a uniformly distributed load, and I want this load, I can choose it to be applied at the centroid location of the element, or I can choose it to be applied at the top of the girder where the nodes are actually created. So if you want it to be applied at the centroid, you can check on eccentricity. If you want to be applied at the top of the member, you can check it off. So right now I'm just applying it to the top of the section. So I'll check off this eccentricity, and let me just quickly click on this toggle button and select the elements on which I want to apply. So this button toggles between the current dialog box and the works tree. I'll come to section and double click on the girder members so they are selected. I'll click on this toggle button again and check off eccentricity, enter the values, which is minus 0.5 kips per fit, and then click apply, and you can see the load applied onto the structure. So once we have defined these two loadings, I'll move on and apply the live load. And before doing that, I need to define two structure groups. So what I'll do is go to the group tab, right click, select new with 3 dots. This allows me to define multiple structure groups at the same time. I'll click on this and enter the name as cross beams. So I'll create one structure group that will consist of all the cross beam members, and other as girders that will comprise of all the girder members, and then click close. Now I'll come to the works tab and then double click on the girder section so all my girder members are selected. Now I'll come to the structure group, click on girders, drag it over the screen and drop it. The moment I do that, you can see all the girder members are defined into this structure group. If I double click, you will see them activated on the screen. Now you might be thinking that number of nodes is equal to 0. Does that mean there are no nodes in this group? And do we need to define them individually into this group? The answer is no. Whenever an element is included in a group, the corresponding nodes are automatically brought in with that structure group. So all the nodes, if you just right click and select active, you will see all the nodes along with their girders activated onto the screen. So this means the nodes are tied with the elements in this group. Let me activate the entire structure. And now I'll come back to the works tab and select all the diaphragm members and the bracing. Let me unselect this. I just need to select all the cross beams and the diaphragms. So what I'll do is double click on the diaphragms and then press down the control button and select all the dummy beams. And now I want to select the bracings. So the best way of making the selection will be selection by plane. If you click on this icon and select XY plane and click on any point in that plane, the entire plane will be selected. This will include all the nodes and all the elements that I want to select. And then I click close, go back to groups tab, click on cross beams, drag it over the screen and drop it. So this will have all the elements and the nodes that are included in this cross beam group. Now I'll move back to the works tab and then start defining the live load. So for this there exists a lot of ways of reaching the live load. You can just right click, go to loads and then go into the moving load analysis data and then click on moving load code and select #to LRFT, click OK. Or you can directly make use of these shortcuts that are given right in this tabbed toolbar. So you can click on moving tab and then you will see all the options regarding the #to LRFT live loads shown here. So what I'll do is select the first option, which is define traffic lanes. I'll click add to define the traffic lane, but let me just activate the this girder plane. So what I'll do is select by plane and this XY plane and then select this plane and activate it. I realize I made a mistake. Let me close this and come back. So if I double click on the cross beams, I notice I have selected all the girder elements also, but I just wanted to consider all the cross beams. So what I'll do here is unselect everything and double click on just the girder group, right click and select inactive so that they are hidden from this display and only cross beams are displayed. And now what I'll do is click select all, which will select all the cross beams, and I'll come to cross beam and then drag it over the screen and drop it. So this will modify my cross beam group and now it will have just the cross beam members. So sorry about that mistake, but this goes to show that how quickly you can mend your mistakes. So I'll activate the entire I'll activate the previous display, and now come back to select by plane feature, select XY, and then click on this tab and activate it. Oops, I clicked on inactivate. Let me activate the entire structure. Select the plane and then click on activate button. Click close, and now continuing with the lane definition, I'll click add here, enter the name as L1 as lane, enter the eccentricity as -6 feet, and the vehicular load distribution can be taken into account through lane elements or crossbeam. So I'll select crossbeam, and here I've selected the structure group as crossbeam, and there is no skew. You can select the make the selection from where the eccentricity is being defined, which is the center girder in our case. So you can either go and click on each and every element to define the layout, or you can do it through numbers. Since it's a curved geometry, I'll go to the top view and display the element numbers. And now if you look closely, you can see 41, 42, 43, and so on and so forth up till 80 is the element number with respect to which we want to define the eccentricity for the lane. So I'll enter 41 to 80 as the element number, and then click add and click apply. So you can see with respect to this girder, you have defined the lane layout. I'll change the name from L1 to L2, change the eccentricity from -6 to +6. Everything else remains same. I'll just delete this table which I created, and then click OK. Sorry, click add and then click OK. So you'll see the second lane also created. So these two lanes are created here. I'll click close, and let me undisplay the element number. Now as per AASHTO LRFT clause number 3 of live load application, where you need to maximize the negative moment over interior piers and take out the axles that reduce the negative moments, and place two truck vehicles on at a given spacing on either side of the interior support. So to take into account these kinds of clauses, Midas Civil has two special features called lane support negative moment at interior piers, where you have to specify the structure group that comprises of girder elements that are spanning on either side of the interior support. So when I click here, I select the entire structure group, click add, and then let me unselect everything, and then and let me activate the entire structure. And then I need to specify the second thing, that is I first specified what is the members that are contributing to this span. Now I need to specify where exactly is my interior support location. So I'll click on this option which reads as reaction at interior support, and then I'll use a single select tool and select the base of the pier, because all the supports are lying in the same line, and then click apply. So now the program knows in which plane the supports are. Then click close, and the program will optimize the placing of the vehicle in such a manner that it maximizes the negative moment over interior piers. Then I'll click on this green icon to create the vehicles, and I'll click add standard, and here I'll enter AASHTO LRFT load as HL93 truck, the dynamic allowance factor as 33%, and click apply. Then I'll change it from truck to tandem, the DLA remaining 33%, and then I'll click OK. So two vehicles have been defined. I'll click close, then I'll click on the second icon, which is to define the vehicle class. I'll put the two vehicles together in a class called VC, let's say, or HL93, and then select the two vehicles and put it here. Click OK and close, and then I'll define the vehicle class load group as add, and it will be MVL, moving vehicle load. Click add and select this vehicle class from 0 to, and minimum number of loaded lanes being 0, maximum being 2. I'll select the 2 lanes and put it here. Click OK. Now what the program will do, it will go through all permutation combinations and find the maximum or the worst loading case for you. I'll click close here, and now move on to assign the moving load analysis control data. I'll go with the default settings. Basically, influence line dependent points are is the one that results in maximum bending moment or the maximum forces. Uh, 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 Basically, it will apply the vehicle in such a manner that it maximizes the bending moments in both positive and negative zones. And with this option, normal plus concurrent force, you can generate not only the envelope result but also the concurrent forces, that is for a given bending moment what is the corresponding shear and axial force. Then I'll click OK, and now I'll go ahead and define the response spectrum analysis data. For this, I'll first convert the mass into load. So I'll go to structure type and select convert self-weight into masses, then click, and also I'll choose the option called lumped masses, consider off diagonal masses. What it does, whenever you have used a section offset and the node is created at the top, and if you don't check this option, the mass will be converted, the self-weight will be converted into mass and lumped at the top of the girder. But for seismic analysis, if you want, and if this offset is large enough, you can choose this feature and have the self-weight converted into masses and lumped at the centroid location for the section. So with this feature you can achieve that easily. Click OK, and then go to model, select mass and select load to masses, and convert the superimposed dead load that is there onto the structure into load, and then convert that into mass. Click OK, and then you will see this kind of icon representation. And now you can go ahead and define the response spectrum. So right click, go to loads, select response spectrum analysis data, select response spectrum function, click add, and you can create your own set of files or copy paste your data from spreadsheet. You can just import a file with response spectrum data in it. Click open, you will get this data brought in. I'll name this as RS, as response spectrum. You can enter a description. It's as per AASHTO LRFT. You can specify site and soil condition, etc., etc. Then click OK and close. Then I'll go back to loads, response spectrum analysis data, and I'll select response spectrum load cases. And here you can enter the load case name as RS-X for X direction. In the XY plane, excitation angle being 0. You can choose your modal combination to be based on SRSS, CQC, absolute or linear. You can also include the positive and negative signs, and in order to get more details you can just hit F1 from your keyboard and it will take you to the online help page and describe all these features in detail. So I'll not dwell much into this since we are running out of time, and I'll select the response spectrum that I have defined with a damping ratio of 0.05. If you want to add separate damping values at each and every individual mode shape, you can use this feature to define that damping method. You can click here and select what type of damping you want to apply in different modes, but right now we'll not dwell much into this. And then click add. This is created. I'll create another load case for Y direction, that is global Y. The excitation angle will be 90, and then click add. So we have defined two functions. Now we'll enter the eigenvalue analysis control. Click on this button select, you can select different variations. So I will select land shows and enter the number of modes as, let's say, 10 to start with. Click OK and then click close. So once you have done this, you are ready to perform the analysis. I'll just click perform analysis, and or rather in order to save a couple of seconds here, I can open the file which has the analysis already done. In the meantime, while the analysis is running, so let me bring up the model file, click open and select the final file. So now if I this is the analyzed file, and if I turn on the solid view, I have added some colors to it so that it's more visually enhanced. And now let's quickly go through some results. So right click, I'll go to reaction, forces and movement. First we'll verify whether our loading is correct or not, so we'll just check for self-fade. I'll click on this button and select self-fade and click OK. So now you can see all the loading is in the vertical direction, so you're getting a summation in F for Fz, while Fx and Fy are 0. And if you can do the number crunching yourself, you can compare whether this value is correct or not. So this ensures a proper flow of forces from top to the bottom of the structure. Hence the loading can be verified. Then you can come to the deformation tab and just check on the deformed shape, or let's say displacement contour. You can select deformed shape legend and you can click apply and see the deformed shape as shown here. It's a bit exaggerated. Let me put it to like 0.5, but if you see the scale, it's if you see the values, it's just 0.004. so let me change it from foot to inch. This is about 0.5, half an inch is the deflection you can see. And as you can see, the outer girder is suffering the most because of the curvature and the extra length. And now I'll come to the forces and select beam diagrams and see the self-weight bending moment. So I'll select fill, check off deformed and click apply. And as expected, the outer girder will be attracting maximum stress value bending moment because of the extra length. So all these go to show that the through deformation we can ensure that the nodes and elements are properly connected. The through bending moment diagram we can see that we can quickly check whether the diagrams make any sense and the model is correct or not. So once we have we are confident that the model is correct and modeling there is no modeling error, we can quickly see some other results like bending moment due to live loads, the bending moment envelope. Click apply. So this is the positive bending moment envelope that we are seeing, and as you can see the outer girder is having maximum bending moment. And similarly you can see for negative bending moment envelope, click apply and you can see the bending moment. And if you are curious to see what loading pattern cause the maximum negative bending moment at this location, you can just right click, go into moving load tracer, select beam forces and moment, and then select that MV minimum, that is maximum negative bending moment, and click on that element in particular and click apply. And then if I zoom out a bit, you can see that there are two set of vehicles on either side of the span, and the blue color loading is the lane load, and you can see the 3 axles and 6 wheel locations. And if you notice, the value is 14.4 kips, which is 90% of the wheel load, that is 90% of 16 kips. So the program has reduced the loading value as per the code clause and applied it. So through this you can quickly verify whether your loading pattern or the analysis or the live load analysis makes any sense or not, or if you have done something wrong in modeling. So in this way you can verify your results visually. If you want to see the influence lines for, let's say, bending moments and forces, let's say for one of the line, and I want to animate it, so I'll click Let me turn it in this direction so that you can see how the vehicle is moving onto the structure. Click apply, and then I'll click record button, and the program will uh, show you the animation for generation of influence line, and there you will be able to appreciate how the complete 3D geometry is playing the role in transferring the moments from one girder to another and from girders to the pier cap. And I can see some viewers asking questions, so what I'll do is hold on to these questions, and since we are overshooting the time, I'll reply them individually in an email. So while this influence line is being generated, I'll quickly open the analyze model that we were doing in the first place, and the total analysis time was 30 seconds, and I'll show you the vibration mode shapes in the meantime. So I'll come to result and go into vibration mode shapes, and now here I can select, let's say, mode shape 1, and along with the legend the program will show you what is the percentage mass participation. This is the first mode shape, second mode shape. You can choose to display multiple mode shapes in the same time. So let's say I want to see 4 mode shapes. Click apply, and the program will divide the entire screen into 4 parts. So mode 1, mode 2, mode 3, mode 4 are shown simultaneously, so you can see different mode shapes in the same display. Let me close this. So once you have verified the mode shapes, you can see them in a tabular format also. So you can see the 10 modes and the modal participation in different axes. So you can see for X and Y it has reached 97 and 92%, and Z it's falling short. So you can choose to go on with the eigenvalue analysis, let's say next time 1 to 20, and in this manner you can see and find out how many mode shapes will be sufficient for this type of bridge. And you can also visually and through these numbers verify which will be the principal mode in different directions. For example, if you see here, you are getting very low participation for the third mode shape in Z direction. So let me go to third mode shape and click apply, and if you see from this angle, you can see that the mass that is going above this neutral axis for the bridge and below the neutral axis of the bridge is almost equal. So therefore this mass is cancelling each other. So if I were to choose the principal mode shape for Z direction, I would have gone with the results for this mode shape instead of going for the fourth mode shape, which will look like this, as most of the mass is above the neutral axis, so you're getting a good mass participation value. So through this visual interpretation, you can make out which happens to be the critical mode shape or the principal mode shape for a given axis. And this is where the software has its advantage. Now I'll show you how you will get the capacity for that for a given section. Let's say I want to have it, see it for piers. So let me right click or switch to the initial view, right click, go to deform displacement contours, and activate just the pier assembly, and use let's say in the X direction, right click, click on deform and legend, and this is the displacement that is occurring during the response spectrum along X-axis, and this is the demand. You can see at the top it's quite less. If I convert into inch, it's about like 0.004 inches. You can see it in the Y direction also, and this is the demand in the Y direction. So in this way you can easily extract the demand values from response spectrum. Let's see how much is the pier deforming, and if you want to see the global picture, you can activate the entire structure and see the global picture. Again, it looks exaggerated, so you can reduce the scale to get a more realistic display. You can even animate these results. So this is how you can extract and do the response spectrum in Midas Civil. Let me come back to the other model file where the animation file is completed, and here you can see the influence line animation and the forces that are coming onto the structure, and how the notice how the pier assembly is interacting with the girders. So in this way you can see the true 3D behavior being replicated in the model. So this is all I wanted to share with you today in this webinar, and highlight how the 3D bridge geometry can be generated for curved steel structures and modeling the cross frames, and how live load is applied onto the structure, how geometry is generated by the use of different type of boundary conditions that includes rigid links, supports, and elastic link of rigid type, how you can taper sections and model pier caps in pier, and how you can apply response spectrum, in particular eigenvalue analysis, and how visual interpretation can play a critical role in assessing the governing mode shifts in different directions, and how you can extract the capacity of the structure, and how you can see the verify your live load results in the software, and how you can see whether the program has generated reliable results or not through moving load tracer. So this is all I covered and summarized in front of you. If due to the time crunch I'll not be able to take the questions right now, so I'll put up my contact details for you, so you can reach me at my contact through email or phone, and I'll be more than happy to take care of your questions. Once again, thanks a lot for attending this session. Hope you find it useful.